Hello everyone, welcome you. I want to welcome you in this accompaniment of the LSST at Europe7 conference, which is held in Poland. And today, open lecture will be presented by Dr. Jimmy Robinson from the University of Edinburgh, which he will talk about this LSST, what it exactly means, legacy survey of space and time, and what it means in the local solar system astronomy. So the stage is yours.
Yep. Thank you very much, Jacob. Yes, so thanks very much, guys. I'm Dr. Jamie Robinson. I'm a postdoctoral research associate at the University of Edinburgh, based at the Royal Observatory there. So first of all, I'm very grateful for the invitation to come speak to you today. I get to work, luckily, in a nice old observatory, so it's nice coming to see another old observatory. Very nice to look around here. And yes, what I'd like to do is, we've been here this week having this conference for LSST at Europe. So I recognize some of you from the conference as well, but I want to put it into context, what this upcoming survey is and how it's particularly important for my research area in terms of, asteroids and comets and the solar system. So I thought I'd also give you a bit of context in terms of what I actually do. So in terms of my research, I'm very interested in the asteroids and comets that we can observe in the night sky. But the sort of overarching science questions are, how did these asteroids and comets form in the early solar system? What sort of things are they made of, rocks and ices? And then all together, how can we put together what we know about the solar system to telling us, how did it form? How did the sun and the earth and the planets all combine together and leave us what we see today? I think it's also important to point out that although I've been lucky enough to go and visit some telescopes and use them myself, this is me at the control room for the Isaac Newton telescope in La Palma. My day-to-day work and research is very much more data-based, so I'm not a very good practical astronomer. I'm relatively okay with Python and working with data, but hopefully I'll give you a flavor of, it's still exciting, it's still fun. And yeah, so the general structure of the lecture is going to be, I'll give you an introduction to sort of basic solar system science, talking about how it formed and how that resulted in what we observe in asteroids and comets. Then I want to give you a very brief introduction to the sort of concept of survey astronomy and how telescopes operating in that way gather data. And that introduces us then to talking about the legacy survey of space and time. This is sort of the big new survey that's coming up very, very soon. And then just to give you some examples more specifically of how the LSST will really benefit research in terms of studying near-Earth objects and also interstellar objects. They're very exciting things in the news right now. So yeah, you're probably all quite familiar with this sort of broad overview of the solar system itself. But this figure just shows a schematic of a top-down view of what you would see in the solar system. So we've of course got the sun in the center, and then as we move radially outwards, we have these different regions with the planets. So in the inner solar system, we have the terrestrial planets, Mercury, Venus, Earth, Mars. These are sort of quite relatively small, rocky bodies compared to what we find in the outer solar system, which are much more massive planets containing much more sort of volatile species. So these are the gas giants, Jupiter and Saturn, and then we've also got the sort of icier Uranus and Neptune. But yeah, I'm sure you're all well aware of the general structure of the planets, but then the asteroids and comets, where they fit in is most of the asteroids in the solar system will be found between Mars and Jupiter in this belt containing many, many millions of asteroids. And these are going to be mostly sort of rockier bodies because they formed closer to the sun, where the heat of the sun meant that the ices couldn't be sustained on their surfaces. But again, I think as well, you probably have all heard of the asteroid belt. But then interestingly, beyond the orbits of the giant planets, you have what's known as the Kuiper belt. And this is sort of equivalent to the asteroid belt, but where the asteroid belt is made of rock. the Kuiper belt is mostly made of ice. So this is an extremely large, similar shaped radial distribution of objects, but much further from the solar system, so generally much icier. And then it can't be shown in this diagram right now, but if you then go even further out than the Kuiper belt, you're surrounded by the Oort cloud, which is a spherical distribution of very, very distant, very icy objects. And this is where the comets come from to fall into the inner solar system. So there's been lots of course, work over a long, long time, how did the solar system itself form? But we've started to settle on sort of broad constraints that come together into this sort of picture here. So in general, of course, the sun itself formed out of a cloud of gas and dust that collapsed, concentrating and getting very high density temperature pressure in the center, allowing fusion to happen and the sun to be born. But because of angular momentum, a little bit of rotation in that collapsing cloud, the physics of that means that as you go from a sphere that's rotating, as you go and collapse down, you tend to flatten and form this disk. So the initial planetesimals grew out of this disk surrounding the sun. And so this figure here is just a sort of cartoon view of how this process proceeded. So on the x-axis, we have radial distance from the sun. And on the y-axis, going down, this is us going forward in time. So as I said, gas and dust collapses into a disk. Within this disk, those small dust particles grow into minor planetesimal bodies. And then I had mentioned before that there's this general sort of compositional gradient where closer to the sun, temperatures are higher, you form rockier bodies because the ice is too volatile to survive. So in this schematic, these rockier bodies are denoted by red dots. And then as you get further away from the sun, the bodies tend to be more and more icy. So these sort of dark blue bodies are the iciest planetesimals that formed. And then what happens is there's this process of uneven growth where a small number of planetesimals grow much faster than the other ones. And these become the seeds, the sort of early embryos that the planets form out of. And what happens is, these embryos grow very quickly. They interact dynamically. So these tracks vertically show how the planets moved around and interacted. And basically what happens is, like, Jupiter is a big dominant force here. It goes in and out and shakes it all about. And what happens is those initial planetesimals, which were in that compositional gradient, they're mixed radially. So what we end up happening is we end up with the sort of structure that we see today, where we have the main asteroid belt contains mostly rocky things, but there's a small amount of icy objects that were pushed inwards by Jupiter, whereas the Kuiper belt are just the icier objects that were left surrounding things. So people have done lots of simulations showing this. So this is a top-down view of that system. The giant planets start very compact and close together. They interact gravitationally, and then you saw this big explosion, basically, where that's them settling onto their final orbits, but also throwing out all of these green asteroid particles into their current orbits. And in general, if you want to look up this more, this is called it's not the NICE model, it's the Nice model. It's named after the city in France where the researchers developed it. But this is sort of settling as being like quite a good way of explaining how the solar system formed. And then in terms of what about asteroids and comets that we observe today? That sort of scenario that I laid out means that the asteroids and comets, they're the leftovers of this planet formation process. So they're the leftover chunks, the building blocks. And in terms of what we can measure today, we want to go and learn more about their physical properties. So what sizes are they? What are they made of? What's their structure? How are they rotating? We also want to know where in the solar system we're finding them. So that's what orbits they're on. That's this little diagram here, just showing you a very simple Keplerian orbit where it's an ellipse centered with one of the sun at one of the foci. And sorry, this diagram here is just showing how as an asteroid rotates, if it's not a sphere, we expect this change in brightness. So what we can do is by looking at how the brightness of an asteroid is changing, where it's found today, we combine that all together and we combine that and use that as constraints on the models of planet formation. So how exactly do we know what tracks the planets took? We look at where we find everything after this initial distribution. That's our constraint. And then I really like this thing. I saw this really good paper, serious paper talking about the potato radius, because basically asteroids are so small that they don't have enough gravitational, self-gravitational force to squeeze themselves into a sphere like the rocky planets. So there are a whole range of crazy shapes, and yeah, especially Itokawa here looks just like a potato. So the potato radius is the approximate diameter radius you need to be to start being more spherical than an asteroid. But what I want you to take away from this slide is that there's such a wide range of structures that we can see when we look at asteroids. And so for example, Arakoth here is believed to be an extremely primordial body. It's got this bilobed structure that's very interesting, whereas an asteroid like Ryugu, this is believed to be a much more modern structure where this primordial body has been broken apart. This is like a rubble pile. It's the reaccumulation of debris, basically. And it's in this distinct rotational spinning top. It's got very little internal structure. It forms this spinning top shape.
These are all rocky, right? None of them is an icy.
Yeah, so sorry, I should point out this is a combination of asteroids and comets. So for example, Ryugu is it's a near-Earth object, so it's one of those rockier bodies. Arakoth is in the Kuiper belt. It's one of those more icy bodies, but it stays far out, so it doesn't, it's quite stable. Whereas Comet 67P, you can see here the jets coming off of it. This is something that comes from the outer solar system into the inner solar system, and the ices sublimate.
I have one question.
Yes?
How can they get
course.
an image of the comet directly like this?
Yes.
Without being affected by, I thought the coma would sort of shroud the comet.
Yes, so these are all images from spacecraft missions. So yeah, directly imaging and resolving the surface of the comet. That was an issue with planning, I think, these missions to a comet, because as you can see, there's activity. The gas and dust is lifting off. It makes a very interesting environment. So yeah, I think they had to be quite cautious with the Rosetta mission with how close they could get. But they did pass through the coma to collect measurements of the volatiles and dust inside. And then this slide here shows some of the same objects, but whereas this is showing them all at roughly the same visual size, this is showing them in actual true scale. So there's a massive range of sizes when it comes to asteroids. And what I also want you to take away from these two slides is this is all images taken with spacecraft visits. So obviously we learn a lot of what's going on with what these are made of, what shapes they are, what their structure is. But spacecraft missions are incredibly expensive, and this is all of the images we have for asteroids and comets. So what I'm going to try motivate to you at throughout this is that this is the value of using big surveys. Is we were trying to infer all this stuff about size and composition from photometric measurements rather than directly resolved images. And that brings me on to sort of the general concept of survey astronomy. And I feel like it's interesting to point this out because in general, I think whenever you think of traditional astronomy, you think of visiting a telescope in person, going there, pointing at your target, taking data. So this is me at the Isaac Newton telescope in La Palma. This is a telescope that we would have used to go and get these sort of measurements of asteroids, getting their brightness as a function of time. And this data is from the Danish telescope, another telescope we use, but this is showing what we do. We basically have a single target that we point this huge telescope at for an hour or something and get this nice light curve showing how it's the asteroid is rotating and changing in brightness. And this is great for looking at this high cadence, well sampled light curve. It gives us a lot of detail for a single object, but obviously this is then like sort of a low volume of your sampling. So in terms of we're getting to this stage where that would have been fine a few decades ago when there was a limited number of asteroids actually known, but now there's more and more being discovered. So this is starting to get to the stage where this type of targeted observation is getting inefficient. To do the science at the volume that we really want to proceed at. So yeah, over the last few decades, more and more telescopes are being devoted over to survey observations. So this figure here shows a map of the sky, and the colors are showing a particular observing pattern for one of these large surveys. And basically what happens is, the telescope doesn't have a particular target in mind, it just scans the sky in some cadence. So in general, what you're doing is, because you're covering a larger area, you have like less time coverage, you can expect less detail for any given target, and you're not necessarily gonna get like a certain asteroid appearing in the right field of view at the right time. So they're serendipitous observations, you just get whatever happens to be in the field of view of the telescope at the time. But the cool thing about that is it's high volume then. It means that you can start to sparsely sample a much larger population of objects. And one of the things I find really cool is that a survey may have a particular science goal in mind that influences where it's looking on the sky, what filters it's using for its observations, how often it revisits a particular bit. But because a lot of surveys then end up putting their data in like a nice publicly available archive, there's a lot of opportunity for, someone might have done a supernova or a galactic survey that I can then search for asteroids, or vice versa. There's a lot of synergy that we can get involved in. And this then brings us on to the LSST, or the Legacy Survey of Space and Time. So basically, this is this huge upcoming, it's here. It's been being developed for quite a long time. So like I started doing my PhD in 2016, and I was told like, oh, this is coming very, very soon. And that's like, I'm a late addition to the LSST sort of club. People have been planning this for decades. So it's really exciting, even just for me, seeing this coming into play. But essentially, the Legacy Survey of Space and Time, this is going to be that survey that's going to be taking place. It's going to be conducted at the Vera C. Rubin Observatory. And the plan is that starting very, very soon, I think possibly as early as October 2025, it's going to scan the entire sky for 10 years. It's got the largest camera ever built. And it's going to be basically making this huge cosmic movie that's going to cover a whole bunch of different science. And it's also, of course, really important to point out that it's the Vera C. Rubin Observatory. It's named after a famous American astronomer, Vera C. Rubin. She was one of the first people to put forward this evidence in terms of galactic rotation curves, I think, that shows that there's this need for dark matter and dark energy. And it's sort of interesting that this is we're in 2025. This is the first observatory that is named after, first major US observatory named after female astronomers. So, it's quite important to make sure that we don't lose sight of the important work that all sorts of people have done in the past. For me as a researcher, this is quite interesting though, because if I write a paper, I have to be very careful about exactly how I do the nomenclature. In terms of they're very specific that you have to say, it's the Vera C. Rubin Observatory, or there's very specific ways of doing that, but I think it's all for the best. It's protecting the brand of the telescope, so that's good. In terms of the physical observatory itself, so this is, of course, a big American project. They're the ones that have funded and built most of the telescope and the instruments, but naturally it's being built in Chile. So Chile has some of the best astronomical observing sites in the world. It's got these sort of very dry, deserty, mountainous regions. So there's very little moisture in the atmosphere. You're very high up. You're sort of above most of the turbulence. So it's some of the best astronomical sites in the world. And then, of course, wider than just the US and Chile. This is why LSST at Europe conference has been happening this week. It's this big international collaboration. Even though like for example in the UK we haven't directly built anything to do with the telescope, I don't think, but we're contributing analysis software. Other countries are contributing different things, and it all brings us together to get access to the data that's coming. And then what's the idea? Like what makes this the LSST at the Vera Rubin Observatory new and exciting and different? Well, it's the largest digital camera ever built. So it's got this amazing high resolution, incredibly wide field of view. The telescope mount itself is, it's a technological marvel. It's this huge, massive structure, but it has to do this survey very quickly. So they've got this huge thing moving, in the order of seconds to go point in a different part of the sky. And then, the light gathering and like sensitivity of the camera means that we're going to be seeing features in the sky that are much, much fainter than we've ever looked at before. And because all of this is coming together, constantly running for the next 10 years, what we're effectively going to get is this huge astronomical movie. So we have a little video to show. So this data comes from the Rubin First Look event, which was a few months ago, where they released the first public data coming from the telescope. And it highlights the discovery and presence of asteroids in the images. So what you saw first is one object, then many more objects. Altogether in this data release, there was 2,000 new asteroids discovered. These objects weren't known before because they were just so faint. So this shows the sort of whole, there you go. That's the whole field of view of one Rubin image, and these blue dots show the discovered asteroids moving through on their orbits. So this is just a small part of the overall survey. What this animation here is showing, you might be struggling to see a little bit, but as the Earth goes around in its orbit and Rubin accesses different parts of the sky, it'll be sampling these concurrent wedges of the asteroid belt. So there's going to be huge numbers of asteroids discovered. Thank you. And yes, that's this sort of the getting onto the actual survey part of it. So we have the survey that's being conducted at the Rubin Observatory is this LSST. And the idea being is that it goes through the entire accessible sky from Chile. So it's sampling primarily the southern sky. It'll revisit the same field at least twice in a single night and then come back again in 3 nights' time. It'll do this same pattern for the next 10 years. It's important to note as well that it'll cycle through in different colors. So for example, whenever we use different filters at a telescope in astronomy, these different filters are really, really valuable for giving us extra science in terms of like for asteroids, different compositions will have different colors. And yes, as you saw from the asteroids moving across the sky, that gives you a sense of, this sort of, although we're taking all these individual images, when you put all that together at the end of 10 years, you're getting this long video, basically, of how the sky has changed. And the cool thing about, LSST is that it's not specifically designed for, one single science case. It's got these main sort of 4 science pillars that it's going to be covering. So of course there's the solar system science side of things. So the primary solar system goal is to discover as many new asteroids and comets as possible. In addition, there's the sort of transient, what changes in the sky. Because basically as the survey goes on in time, it'll pick up anything that's changed from the last time that it had visited that same part of sky. So this is going to be really relevant for like supernova, AGN, like all these sort of things in the sky that are changing. And in addition, this is going to provide really good maps of the stars in the Milky Way and distant galaxies that help constrain cosmology. So there's all these different science areas that sort of come together into this one big survey. And yes, so I mentioned the changes in the sky. The way this is actually going to happen, it's a technique called difference imaging. So every time the telescope takes a new picture, it goes into its library of past pictures and effectively subtracts the past picture away from the new image. And what this should do in principle is, like, for example, if an asteroid is moving across the sky, it appears as a new source because it wasn't there in the sort of static sky picture, or likewise a supernova all of a sudden goes off. It wasn't there before. So these are going to be coming together as these what's known as alerts. So every time the telescope takes a picture, searches for all these new things, either asteroids, supernova, whatever, it'll in real time effectively issue an alert to the science community. So if I'm interested in like a really interesting asteroid, I'll be like on the lookout for interesting asteroid alerts. And yeah, to give you a sense of the data volume, there'll be up to 10 million of these alert detections issued every single night for this 10-year cadence. So there's going to be this huge amount of data. And then in terms of the wider survey, we can expect at least 800 sort of revisits to every given point of sky over the full 10 years. So there's going to be a huge data set. And in terms of what makes this actually possible, pretty much all of these three main aspects of the observatory that are required to allow this survey to proceed are quite cutting-edge technology in their own right. So we've got the camera, this huge detector, biggest camera ever built. The telescope itself has this really interesting design to allow it to do this survey. And then to enable the actual science to take place, there's a lot of sort of less glamorous, I guess, but very important work going on with data servers and making sure that we have the capability to work with this huge data set as well. So yeah, I mentioned 10 million alerts. That's 20 terabytes of data altogether in a single night being taken by this telescope and sent to these different data centers. In terms of the camera, it was quite interesting because if you go on the website for the lab that built the camera, they're very specific and say this is the largest astronomical camera built in the world. So I don't know if that means they've built a secret other camera that's on some satellite somewhere, but who knows. But yes, it's effectively 3,200 megapixels. It's actually sort of broken down into this array of smaller detectors that come together to make this one big camera. So each of these blue squares is an individual CCD detector. For the purposes of the camera itself, they're like subdivided into these 3x3 rafts. And then, yeah, all together, there's 189 detectors taking data every time the telescope takes an image. And just to give you a sense of how big and wide angle this is, 3.5 degrees across for the field of view. That's what the moon looks like in there. So this wide field of view allows explains the sort of huge amount of data being taken with every single visit, and how this telescope will be able to cover this huge amount of the sky. In addition, I think these are the filters sitting outside of the camera. So it'll have 6 color filters going from like the ultraviolet to the infrared, U, G, R, I, Z, Y. So these filters will be sort of slotted automatically into place according to the survey schedule, and give us, as well as the brightnesses, brightnesses in different wavelengths, giving us all this additional information, which is really valuable for the science. And yeah, these are some of the biggest filters built for astronomy as well. This is all pushing the boundaries. In terms of the telescope mount itself, yeah, it's got this quite interesting setup, because I think the The overall diameter of the primary mirror is 8.4 meters, but it's got this very interesting optical design where this sort of, it's an annulus, it's like a ring, and then in the center of the primary mirror is actually where the tertiary mirror is located. So, light comes in, bounces off the primary, goes to the secondary, into the tertiary, and then into the camera. So effectively, although it's 8.4 meters diameter, in reality, I think like the actual collecting area of the telescope is something like 6.7, equivalent to a 6.7 meter diameter telescope, but still this is incredible. As I said, the mount itself is massive, 300 tons of steel, this huge, it takes a whole building to house this structure. And this has been engineered to move incredibly quickly. So I think altogether between taking an image, which the exposures will be about 30 seconds or so, and it getting to the next part of the sky to take the next image, it'll be about 40 seconds altogether. So this thing is moving from one part of the sky to the other in like 10 seconds. And that's the thing. I've only been to a telescope a couple of times, much smaller than this, and seeing this huge amount of metal moving around makes you very glad that you're not in the dome with the telescope when it's moving. Health and safety first, stay in the control room. And then, I mentioned the data. This is like one of the things that sort of, well, I wouldn't say concerns me the most, but it's one of the biggest challenges that we as researchers are going to face. Because this telescope is, the camera is so high resolution and big, this is why we're expecting up to 20 terabytes of data every single night, 500 petabytes for the whole survey by the end of 10 years, and trillions of these individual detections. And like that makes for this sort of alert stream problem in a way. Is this going to be an alert stream coming to my computer, or is it going to be a tsunami? I've also heard it described as the fire hose. As soon as the survey starts, it's like opening the fire hose, and we're going to get huge amounts of data coming in. And then, in terms of like the alerts themselves, the processing going on behind the scenes with these with the data pipelines means that within about sort of 1 to 2 minutes, that image that was taken will be reduced, difference imaged, processed. It'll go through all of the different science pipelines, and these alerts will be being issued to the public within 120 seconds, basically. So it's incredibly fast turnaround of data. In addition to the alerts, there'll be the sort of catalogs of data coming in. So those initial prompt products, as they're referred to, will be coming to you within like 24 hours of access. So for example, with solar system science, one of the prompt catalogs we'll be interested in is what are the new orbits that have been detected for new asteroids and comets. And then after an embargo time of about 80 hours, we'll have, as researchers, we'll have direct access to the actual pixel data as well. This will be really valuable for like if I wanted to go, is this new asteroid, is it actually a comet? Is it active rather than passive? I can go and look at the data itself and do my own analysis. Although it's important to note as well that like in the sort of previous surveys, the volume of data being produced it was always like, it was big at the time, but past surveys you could easily, like if you really wanted to, download all the data onto your own computer or like server at your university and work on the data yourself. With LSST, just the numbers are too big. You're never going to be able to do this. So they've got all these automated systems like the Rubin Science platform that allow us to interact with the data coming from the survey. And then, in terms of the alerts, the alert stream, we'll have to, as users, go and access them through what's called an alert broker. So basically, the telescope takes an image, it gets processed by the Rubin Observatory, and then they make their alerts, and the alerts get sent to a variety of different brokers. And this, for you and me, is basically going to be a website where I have an account, and it tells me like, oh, you're really interested in solar system alerts, here's some solar system alerts. But the cool thing about this alert broker system means that all of these alert data are fully public. you have to be a data rights holder to get access to sort of like the raw data, the catalogs that are being produced, but like anyone can go and sign up for an account with one of these alert brokers basically and have direct access to, get access to all of the information that's contained in these alerts. So I think this is going to be really valuable for sort of spreading, like for researchers that are in countries that maybe don't have data rights, but also for, interested citizen scientists. They'll be able to do really interesting work and look at the data coming through. And yeah, that's sort of summarized here. The sort of ethos of the survey is to be as like open as possible. And then I'll talk a little bit more about this towards the end of the talk, but you may be aware of a concept called citizen science. So this is where, you might use something like the Zooniverse platform, which I'll mention briefly later. But basically, I have all this data. I have too much data for me to analyze. How can I get, interested citizens to help me with looking at this data and do some actual, research? There's a lot of really interesting things going on there. And then, yeah, so that's sort of trying to give you a very broad overview of LSST. Now I want to be a bit more specific with what's going on in terms of asteroids with LSST. So I mentioned before that the survey as a whole will rely on this concept of difference imaging. So for an asteroid that moves across the sky, you can, in general, the stars and galaxies, they're static against the sky coordinates, whereas asteroids, because they're moving on orbits around the sun, they'll be seen to be moving relative to the background stars and galaxies. So what happens is over a period of time, these individual detections will trace out like a path across the sky. And this schematic here is effectively showing how the pipeline run by Rubin for the LSST will take these like individual detections and link them together to find candidate asteroids and comets. And it relies on this sort of 2 + 2 + 2 method where, let's say the first night of data, I mentioned before, the telescope will always revisit the same part of the sky at least twice in one night. So in between the telescope first visiting and second visit on that first night, this asteroid has moved a little tiny bit. But of course, it's really hard to tell. Like, you can't tell you that one thing moving in one night is definitely an asteroid. So what they do is they come back a few nights later on night 2. They take images of that similar part of the sky again, and then in this case they visited 4 times. This is just for the purposes of that diagram. But what happens is that we've seen this object starting to move across. You can start to say like, okay, this is pretty convincing. I can draw a line through this. But what's required to really make the detections sort of pure and get rid of any false positives is a 3rd night is required. And there's this fancy algorithm that goes through and initially tries and finds pairs of detections that are nearby each other in each night. That makes these pairs into what's known as tracklets. And then a similar routine then takes tracklets and tries and fits wider like sort of arcs of motion through them to form tracks. So right now the pipeline has gone like, oh, I found a really interesting track. This looks like a moving object. What happens is the survey, the pipeline automatically issues these detections to the MPC. This is the Minor Planet Center. And the Minor Planet Center is sort of an independent entity that, for decades has dealt with asteroid and comet discoveries. They say like, oh, okay, we'll fit an orbit to this. Once they get a good orbit, they feed back to the Rubin pipeline, and then Rubin now knows this is a known object, and then any subsequent times it sees it, it can attach its detections to this known object, and this is how the catalogs get built up. And then I mentioned already that, yeah, LSST, through this discovery pipeline, will discover huge numbers of objects. What this table here highlights is for different dynamical classes. So the really important one to look at here is the main belt asteroids. This is the most numerous dynamical class of asteroids that we know about. Currently, in the Minor Planet Center catalogs, we have 650,000 known objects, quite a lot. LSST by itself, over the 10 years of the survey, will discover 6 million objects. So, we're getting an order of magnitude increase in the number of known objects. This is going to be, and this is across all of these different dynamical classes, basically, either a factor of a few or a factor of 10 increase in number of objects. So this is going to be amazing for our science. And then I mentioned the 4 different science pillars. So one of the things that I want to emphasize here is that, my speciality obviously is asteroids and comets, but this sort of method of discovery for moving objects, it's sometimes in contradiction to another science case. So for example, supernova, this video here, which should start shortly, shows what a supernova looks like in a background galaxy. So this little dot here, I think this will replay a couple of times. So it's this little faint nothing that gets much, much brighter and then fades away. This is a sort of like light curve of what that looks like. So over the course of a few days to weeks, there's this, something in a galaxy just goes boom and emits all this light. But these are static in the sky. So a supernova person is much more interested in, like, once a supernova goes off, they'd really like to get like this full light curve covered. So that's just one example of one of these science cases that is sort of contradictory to asteroid discovery, which wants to scan as much of the sky as quickly as possible. But I just wanted to highlight that to show how, the overall observing strategy of the survey has to balance these different needs. And this is the result. So this is a map of the sky, showing showing the number of times that each little pixel of sky is visited by the survey. This is just for the first year of the survey, so that's why it goes up to 100 or so visits. But obviously, it's like time is a resource when it comes to a survey, so they've had to be very careful about exactly how they divide their time across the sky. So it's not illustrated here, but if you imagine a line going up here and coming back down, these two sort of arcs, these describe the galactic plane. There's a lot of, it's the plane of our Milky Way. There's a lot of people that would be like, oh, I'd love to get more of the galactic plane, but first of all, the northern part of the sky isn't accessible from Chile. Secondly, the overcrowding of stars will make it quite difficult to extract science, even with a camera as brilliant as LSST. So they have a slightly fewer visits covering the galactic plane. And then likewise, this bulge here, this is the north ecliptic spur. So if I was to continue this on as a sinusoid, that would describe the plane of the ecliptic, which is the plane of the solar system. So we'd expect to find most of our asteroids and comets around this region here. So for example, even though the rest of the survey is mostly cut off at this declination here, like the survey was kind enough to grant us a bit of extra space in the north ecliptic spur to boost our discovery numbers. Although you can see that there's a compromise. We don't have as many visits in this particular part of the sky. But overall, the data set is going to be great for these 4 main science pillars altogether. So the last thing I want to talk about is some specific solar system science cases that I'm interested in and that are really going to be helped a lot by LSST. So one of the ones, I was talking to some people before the lecture, it's always easy to get funding as a solar system scientist because you just talk about scary near-Earth objects. So these are objects that originate in the main asteroid belt. So this figure shows a top-down view of the inner solar system. So you've got Jupiter, Mars, and then these dots are the main belt asteroids. If we take this top-down XY view and convert this into orbital elements. So essentially, semi-major axis is that radial distance of an orbit. The eccentricity is how non-spherical that orbit is. So, is this the wrong way around? Maybe. No, ignore that one there. I was cutting and pasting different figures. Down here is eccentricity 0. So that's a circular orbit, and then eccentricity is increasing up to 1. You're getting more and more elongated as an ellipse. But what this is showing is the orbital elements of, in this region here, this is the main asteroid belt, and then this region here is showing the near-Earth objects, so named because they come much closer to the orbit of the Earth than something in a nice circular orbit out here. And how this happens is these resonances, primarily with Jupiter, but also Saturn has an influence. You'll notice that there's an underdensity of asteroids along these lines. And these are basically areas where asteroids are being cleared out by this dynamical resonance with the giant planets. So what happens is something gets kicked out of its nice circular orbit. It evolves onto these more elongated orbits. It probably has more encounters with other planets. And the asteroids that started in the main belt on these circular orbits, they sort of get pushed more into the inner reaches of the solar system. And these different curves and denotations of the scatter points, these show as they evolve inwards, they become crossing the orbit of Mars, then they start to approach the orbit of the Earth, and then they start to, go past the Earth inwards. And this is, once they start crossing our orbit, there's always a chance for a collision. So, this comes into the sort of scope of planetary defense, and, why we want to discover as many of these objects as possible before they could possibly impact us. And this is highlighted here. So obviously, we know that the dinosaurs, the prevailing theory of why they went extinct is this huge impact that probably happened around Yucatan. But, the joke I've liked to heard is, I've seen is, the dinosaurs went extinct because they don't have a space program. So what we're doing is, by cataloging the inner solar system, looking out for these near-Earth objects, we're hopefully going to discover some of these things before they impact us. This map here, just to try and give you a sense of, how frequent are these impacts? Because it comes in the news every couple of months that, oh, there was a big fireball over, there was one in the UK a couple months ago. Obviously, you guys are familiar with Marasco. That would have been a huge fireball followed by an actual physical impact. Since the 80s, and this is one of these things where it's like, what did the Cold War do for us? The US government has these super secret sensors that were intended to scan the surface of the Earth. I think they were initially looking for nuclear tests basically, but they would see these occasional flashes of light that didn't correspond to someone testing a bomb. It was fireballs in the atmosphere being detected. So over that time, this is the sort of distribution of geographical location of where these fireballs were spotted, and then the color scheme shows how energetic they were. And it's for some reason, this is in kilotons of TNT, just explosive physics for fun. Reassuringly, most of these would have just been quite harmless, flashes of light. These low energy things, they wouldn't bother anyone at all. And you can notice that there's a lot more blue things than there are as you get to the redder colors. But for example, this big red circle here, this was the Chelyabinsk impact event in 2013. Chelyabinsk was I think it was probably between 15 and 20 meter asteroid that entered the atmosphere, exploded in the atmosphere, and that energy shockwave, I think thankfully no one was obviously seriously injured, but it blew out all the glass in the city. There was people got cuts and stuff. It was relatively scary. Fortunately, these events are very, very rare, but it's something that we want to try and, if we can get forewarning to a given area that we think there's going to be an impact, people could be evacuated, building up this sort of planetary defense concept. And this is something that I get to do in my day-to-day work. So this isn't LSST, this is another survey called Atlas, and Atlas is directly funded by NASA to do this sort of planetary defense stuff. And basically what I get to do is the primary telescopes for Atlas is like a network of telescopes distributed across the globe, but most of them are in 2 telescopes in Hawaii. So in the UK, our daytime is Hawaiian nighttime. So we have this collaboration where as the telescope is taking data, I log onto my computer a couple of times a day and I get presented with this dashboard of candidate moving objects. So I'm effectively working as a human eyeball to see what candidate tracklets are real and need to be forwarded to the Minor Planet Center. So whenever I get this dashboard, it all looks very complicated, but what I'm really looking for is we have a GIF to start with. I can see if an object is moving nicely relative to the background stars. I get the cutouts. Atlas has a slightly different survey strategy to LSST. It uses 4 visits to the same part of the sky over about 30 minutes to 1 hour. But that obviously then, this is what you would do if you were doing an ideal solar system near-Earth object discovery survey. So LSST won't be as good at discovering things as rapidly as something like Atlas. But then again, LSST is covering a much larger area of sky, going much deeper, also doing other science. So yeah, basically I would submit something to the Minor Planet Center, it goes to the Minor Planet Center and they automatically fit an orbit, and if the orbit looks concerning, there's a wider network that this gets shipped out to. But in terms of how is LSST really going to help with NEOs, the real benefit is how deep each individual image is going to go. So the problem we have right now is that something like Atlas doing this rapid discovery, it has a limiting magnitude of maybe 19 or so. So it doesn't, that's still quite good, but it doesn't go very, very faint compared to the much deeper telescopes. So we are actually at this stage where the sort of, I'm the human in the pipeline, but the pipeline is now getting to the stage where if we're lucky, we can get forewarning of a fireball event with about 12 hours of warning time. There's this slowly growing list of small, fast-moving asteroids that surveys like Atlas have discovered just before they're impacted, and we're testing the system and getting faster and faster. But obviously, if you have something like LSST will discover these things much further away in their impact trajectory, which gives us much more warning, and will build up this map of the near-Earth objects to much more completeness, and that's what's shown in this figure.
For
yes?
Something the size of the Chelyabinsk event, how far in advance will LSST be able to find it in a simulation?
I don't have the exact, and I should point out as well that Chelyabinsk was a funny object because I think it came from very low solar elongation. So there will be the occasional object, even though we're searching for these near-Earth objects, there will be objects that come from places we can't point the telescope. So just keep that in mind. This might sort of answer your question. This figure here is showing the expected discovery completeness of the discovered near-Earth object population as a function of absolute magnitude, but they've also got size up here. So obviously the bigger, brighter objects are going to be discovered at a much higher efficiency, and then that tails off much more rapidly as we go down to smaller and smaller sizes. And this is a logarithmic scale, so yeah, that's 100 meters there. 10 meters, we're down in the low discovery percent level. But this is the point, is that we're trying to push that as much as we can. And I should point out as well that so for example, these lots and lots of blue events, they're sort of in the meter size scale. We don't really worry too much about objects that are a meter. We have very little chance of discovering them anyway because they're so faint. We don't worry too much about objects that are, above sort of 100 meters to a kilometer, because even if they impacted, it'd be devastating. But we have very good discovery completeness for these larger objects. It's objects like Chelyabinsk that are in that sort of, yeah, the intermediate range. I almost said sweet spot, but that would go down badly, I think. But yeah, it's the objects that are sort of just big enough to survive the entry into the atmosphere and just small enough to sort of evade the surveys. But this is the point of LSST. LSST will be giving us much greater depth than we've achieved before. And the important thing is it's much greater depth across the whole southern sky. So it'll be really, really valuable. And then the thing I want to talk about very quickly, because I'm aware I'm running out of time, is interstellar objects. So interstellar objects, you may remember from the very first slides, whenever a star system forms its planets, they dynamically evolve and eject out asteroids and comets. But this process is happening not just around our star, but all stars that form planets in the galaxy. So we expect there to be quite large numbers of these interstellar objects, these asteroids that have been ejected from their home system, just floating around on their galactic orbit. And what happens is the sun, as it moves along, encounters these objects and they come past us. And these are really important objects because they give us, so far, if we look at asteroids and comets, we just have a sample, looking at how our solar system formed. These interstellar objects give us a sample of how an external solar system formed. So I had to update this slide since I last gave this talk. So there were 2 discoveries when I last gave this talk. 1I Oumuamua, 2I Borisov, and then recently, I think 1st of July, 3I Atlas was discovered, again, by the Atlas survey. And these objects, we have this growing population of extremely rare objects. So this is really exciting, especially going into LSST. Just to give you an idea of these trajectories, these objects are on highly unbound hyperbolic orbits, so they're just coming in and zipping past. And this figure here just shows the sort of expected distribution of where these things are coming from. The yellow dot here is essentially the on-sky vector of where the sun is moving through the galaxy. So most objects, as we sweep through the galaxy, will get picked up here. And then, I just want to briefly end more or less on 3I Atlas being discovered by LSST, but imaged by Atlas in very early images, imaged in Rubin. So LSST hasn't actually started yet, but this object has just so happened to pass through what's known as the Science Validation Survey. So the Science Validation Survey is, the commissioning test. So we were really, really lucky to get these images of an actual, really super interesting science object before the survey's even begun. The quick picture is, because of the high resolution and depth of LSST, the object, which wasn't necessarily known to be fully cometary at the time, it was shown to be active. It's got this extended coma around it, so it's clearly made of quite volatile ice that's heating up. Speaking of active objects, the last thing I want to talk about is Rubin comet catchers, which is a citizen science project that I alluded to before. But this is something that you can go on right now as a citizen scientist, look at Rubin data, and try and help find things that are not asteroidal, that are cometary. This is a really cool thing. This is the first citizen science project of many that will be coming with Rubin. And I think I'm well out of time, so I will leave my conclusions up here and take any questions.
Do we have a questions?
Yeah, so you mentioned there was on one of your slides it said that it's possible to also detect asteroids by trailing. So is there an estimate of how many asteroids will be found by trailing? Because I suppose these will all be relatively nearby asteroids, things that are moving very fast.
Yeah, no, that's a really interesting point because, I mentioned that the individual exposures for LSST will be 30 seconds. So for most asteroids that are on, distant circular orbits, there'll be no visible trailing. For the near-Earth objects, there will be this trailing issue. Well, not so much issue. If anything, it'll make it easier to detect them because you're trying to link up these lines. There is a problem, though, where, again, it being a United States project, there's a concern about super secret satellites appearing. Because the other thing that is really streaked in any astronomical survey is satellites. So there will be a hard cutoff of 10 degrees per day they won't issue alerts for objects moving 10 degrees per day, but obviously that's a concern for us because near-Earth objects can easily reach these sort of motions across the sky, especially when they're just about to impact us. So it'll be interesting to see how it happens in reality because they have it established in the pipeline that there will be some methodology of if we see a fast-moving streak and we know it's not a satellite, we'll let the community know that it's a near-Earth object, and it'll get passed on to the relevant minor planet center channels.
So that's been worked out? Or?
Well, this is the thing. I think there's a few things in the pipeline where they're just trying to get it working. So this is something that they say they'll fix, but the exact implementation is not finalized as far as I'm aware.
Yeah. But if this object is large and can cause lots of damage, it's likely that it would have been found earlier.
Yeah, there is this balance. So it's not
so I mean, like you said, if it's like a meter or so, you don't worry about it.
Yeah, exactly.
Do we have any other questions?
I have a question. What if something goes wrong? I don't know, something in the camera can went off or something. What's the plan B, or is there a plan B?
No, that's a super interesting question. So I'm not directly involved with anything to do with the actual Rubin project. I'm very much a user of the data. But this is why something like this conference is really valuable. So I was literally talking on the bus to the Creator Tour excursion with someone who's worked directly on the camera. And he was saying to me in terms of the, there's this huge grid of detectors. So to answer your question, yes, something could go wrong, and apparently at least one of these detectors is shorted out. But because they're individual detectors, they're all independent of each other. The whole survey can still continue with even a little. They've allowed leeway for some of these detectors to die basically. But it's compensated for by, it doesn't revisit the exact same part of the sky every single time. It does what's known as a dither. So it is shifted ever so slightly, rotated ever so slightly, so that over time, even if there's a gap, that gap gets filled in by subsequent exposures. So the person I was talking to on the bus was saying yeah, it had cost so much in terms of money and time to take the camera off the telescope, repair one single thing, that this is just within their acceptable losses for now. So there's redundancy built in. I guess if everything went really wrong, they'd obviously have to fix things, but.
So it's just one CCD out of 189?
I think so, yeah. Although I'm not sure how official that is. This was gossip on the bus, so.
We have a question here.
Yes, I have a more general question. What is your opinion on the future of these large telescopes located on Earth when we compare them with the space telescopes with many less limitations?
Yes.
So, what do we need them for? I mean, those located on Earth. Do we still need them?
Yes, no, that is a really, really good question. Because that is a very valid point where it's at the end of the day, we can build bigger and bigger telescope systems, but we're going to be limited in terms of how much we can actually see through the Earth's atmosphere. If you take a huge detector like this, put it in space, you're not looking through the turbulent atmosphere anymore. You're getting near perfect diffraction limited seeing.
We can look in any direction, and here we have this limitation that you mentioned, that we can only observe the southern.
To a degree. Obviously, with most things, the first limitation is cost. So there's lots of valuable space missions that go up, but it costs a lot of money to put them up there. The launch, the payload, the maintenance is a huge problem as well. For example, if something, as we said, goes wrong with the camera, at least we can fix it. The Hubble Space Telescope is an exception. It was in low Earth orbit and was able to be visited by the space shuttle when they had problems with their mirrors and a fix made, but it was hugely expensive. So you have to be really confident that your sort of system is working right from the beginning. And then in terms of the pointing, there's different limitations in space with how things point. So for example, a lot of satellites get put into, a lot of these space telescopes get put into Lagrangian points. These are sort of, neutral points in the Earth-Moon system. And the reason why you put them there is they're nice, stable gravitational locations. You don't then need to worry about keeping your orbit really well controlled because gravity does it for you. But then the problem is, like for example, JWST, it's in this configuration where it's constantly pointing away from the sun and the Earth. So even though, yes, you can access the full sky, at any given moment in JWST, it's limited to where it can point to, you know, that arrangement in the Earth-Sun system. So there's always going to be this trade-off whether or not you like just build a telescope on the ground or build it in space. And I suppose maybe the final point I would like to make about that is I've highlighted that how many, you know, LSST is going to discover a huge number of objects. And I mentioned the problem of this alert stream. We're going to be inundated with new discoveries. So the problem that we're going to have as scientists is how do we prioritize what to follow up? So it's always been very difficult to get like dedicated observing time on a space mission just because it's such a valuable instrument that's, you know, massively oversubscribed. What we need is more ground-based facilities that are easier to access as researchers because we're going to have so many more objects being discovered. But yeah, there's always going to be this balance between build it on the ground or build it in space. I hope that answers your question.
And I think the future is to build on the moon.
Well, yeah, that would be very cool as well.
Very expensive.
Yeah. No, there's a lot to think about with how we could do it.
Do we have any other questions? I don't see any on YouTube also, so if that's the case, thank you again. Thank you very much for attending this lecture. Thank you very much.
Thanks for managing the AV very well. Yeah, sorry, I went on a little bit.
I think it was very interesting and people were very, very engaged in it.
Okay, good.
They liked it.
Thank you very much.
Yes, no, thank you. I think I can give this back now, I presume.